Hi folks, we're in Module 4 now. We're looking at the novice problems. We want to take a look at these first two problems, 1 and 2. In this section, we're going to be talking about hypothesis testing and also trend analysis. So let's go to our problems. Problem 1. You have a business and you rely on these modem routers, and you've got two locations. You record whether or not the locations have to be reset. You don't like to have to do that because, of course, that you lose valuable capacity during the day when you do that. So you collect data on particular days, and you've got 29 days, and a 0 represents there was no reset, a 1 represents there was a reset. So you've got two proportions or means. You could think of them as a mean, an average of this column of numbers. And one has got an outage time of about 30.9% of the time, the other one 58.6% of the time. So the question we have to ask, is there a significant difference between those two locations from a statistical point of view? And we want to know if there is in fact a statistical difference, and then how you would make that decision. So here is the analysis that takes place. We'll come back to it in just a second and see how we got this. But we have a two-sample test, t-test, assuming unequal variances. The reason we use a t-test is because we do not know the standard deviation of the population, and therefore we can't use a z-test. There'd be very little difference between the z-test and the t-test here because the samples are pretty large. But let's be fair, let's be conservative and say we're going to use a two-sample test. And I most frequently use the unequal variances because when you use equal variances, you're also imposing assumptions. I don't want to impose any assumption at all. So here are our two means. The results are that the one-tail t-test is 0.59, almost 0.06, 0.059. And we compare that to p. Since we're looking at a one-tail test here is what I asked you to do. And this number is larger than the alpha value. We compare our p-values to the alpha, and since it's larger, we cannot reject the null hypothesis. If that had been lower, we would reject the null hypothesis. Over here, I've got some tests with Minitab. Let's see how we did the test here in Excel. Let's grab our data. Then we're going to go to the Data tab, then to Data Analysis, and we have near the bottom a t-test, two-sample, assuming unequal variances. Don't use the paired because the paired is about before and after testing. We hit OK. Our data is already in here. I've captured the data from before. J3 to, well, let's just grab it. Let's grab this whole area here. The next column of data is here. I also captured the label, so I'm going to use that. Let's hypothesize that the difference in means is 0. Then we want to output our results, let's say here. I hit OK. And in fact, we get the same results as we got before. 0.059, almost 0.0606. So we're not going to reject the null hypothesis. How do we do this in Minitab? Well, we grab our data again, our locations. We copy it. We go to Minitab. We insert it. I've already got it here. Let's go to the stats, basic stats. Let's go to two-sample t-test. Each sample is in its own column. The default, I think, is that they're both in one column. So make sure if you've got it in two columns, you hit that or put there in that tab. Here's the data that we're going to select. I already had data in there. Let's just take that data out so I can show you the full procedure. Select, grab the second column of data. Well, actually, that one got put into the. Let me do that correctly. So I want to take all this data out from before. I'm going to grab this data, and I'm going to say I want it in this location. I'm going to take the location 2, hit OK. I go to OK, and it returns information. You can see that the p-value here is 0.06, rounded from 0.59, very similar to what we had before. The other thing we can do is we can also do a test for proportions, 2 proportions. It's okay to do it as means, but we can do it as 2 proportions. Let's take the data out of here. Select the data for hit OK. And here we have a slightly different test. It gives us 0.054. And the reason it does that is this is a z-test, not a t-test. So it makes certain assumptions that weren't made before. So if we're doing a one-tailed test, by the way, excuse me, we're doing a one-tailed test, we're going to assume that the alternative is that the value of the single test is going to be less than 0. The difference is 0 versus less than 0. Why? Because we're subtracting row 2 from row 1. L1 minus row 2 is going to give us a negative value, and so when you're setting up your test, you assume that you're doing a negative value. All right, so we can't reject a null hypothesis because of these p-values are larger than our alpha. Let's go to the second problem. In this problem, we've got data that we're trying to relate one variable to another. We've got an independent variable and we've got a dependent variable. Our independent variable is x and our dependent variable is y. So we're trying to create a relationship between these two values, a function. And we're going to map the area first, and then we're going to apply both a linear relationship and an exponential relationship and see how we do this. By the way, here's a linear relationship. You can see that this line runs linearly through the data. Here's an exponential relationship, which is a curve, a very slight upward rise in this particular curve. And then here is the information that describes the function and the r squared. The first thing we ask is get this relationship and how well does the independent variable explain the variation in the dependent variable. Here is r squared of 0.6053. That means that 60% of the movement in y is explained by x. In this particular case, 57.38% of the movement in x or in y is explained by x. So how do we get these graphs? Well, let's go over here, grab our data. We're going to go to Insert, and we're going to find a scatter diagram. So here's our scatter diagram. I can right-click on the scatter diagram, brings down a menu that says Add Trend Line. Gives me an area for information for the trend line. The first one we're going to do is a linear one. We actually want it to display the equation and to give us the r squared. And there's the information that we were looking for. It gives us the functions. It gives us the r squared. What if I had wanted, rather than a linear function, a exponential function? This is 70,459 times E. This is Euler's number, a very important number in mathematics, raised to the power of 3 exponentiated -5. That's multiplied by x. We'll see how we do those calculations in our graph in just a second. Let me get rid of this guy. So let's take this guy out. We now have the relationships. Question is, how do we predict a value of 50,000 for x? What will be the related y that is specified by the relationship, both the linear and the exponential? The linear is pretty simple. We take the coefficient that we got in the picture above, 4.2236, multiply that times 50,000, and add the constant 39,912. Those are all values that were given to us here. In the case of the exponential, it's a little bit more difficult. We take the 70,000 that we got, and then we're going to raise it. We're going to raise E. EXP stands for E to the 0.00003 times 50,000 level. Anytime you have a constant in front of E plus 5, what that really is saying is that you're going to take your 6 and you're going to put 5 zeros after it. If it's a negative value there, -5, you're going to move the decimal point 5 positions to the left. So this becomes a very small number. If I put those numbers in there, you can see that the calculations give us the calculation of a predicted 315,755 for 50,000 if you assume the exponential, and 251,092 if you assume the linear relationship. Okay, that's it for problems 1 and 2.